So in this problem, we're going to examine the speed of the longitudinal wave that you send down a long uniform spring of length L and mass M. So I have a spring, and I grab 1 minute spring, give it a shake. Okay, I'll give it a shake like this, and I'm going to send the wave down. This wave is longitudinal because the coils of the spring oscillate along the direction of propagation, which I call the x direction. So let me establish an x direction first, like this, x direction. Okay, and so the oscillation is along the x direction, and at the same time the wave travels along the x direction. I want to find that speed. Now, the actual process through which I derive this, it goes beyond just finding the speed of the wave. In this process, we're going to apply Newton's second law to the spring, to the wave motion of the spring, and then we can get a better understanding of what this nature of the wave really is. It's very analogous to the derivation of the speed of the wave on a string. That's a transverse wave. All right, so here everything happens in the x direction. Now, first of all, we know that as the spring oscillates, different parts, different coils of the spring will oscillate at different velocity, acceleration, and displacement. And so let me identify first which part of the spring I'm talking about. Okay, since every segment has different displacement, velocity, and acceleration, I can only discuss one segment at a time. And so that's what I'm going to do. I'm going to isolate a little segment here. Okay, this little segment runs between the left edge and the right edge, and it's got a length of dx. Okay, so before the spring moves at all, before any disturbance comes, I have a little segment of length dx. And let's first of all look at what happens if I give this little segment a stretch. Actually, let me stretch the entire spring and see what happens. Like without any disturbance, I'm just, slowly pulling the free end of the spring by a certain amount, and let's see how this segment stretches. Okay, before I introduce any wave. All right, for the entire spring of length L, I know that the total force F equals kx. Right? So suppose I apply the force F, and the other end is fixed. I apply force F to this end. How much stretch will I get for the entire spring? I know because F equals kx, I know the total amount of stretch would be equal to F over k, right? F over k. And that F over k, let's say it equals to 10 centimeters. That 10 centimeters is the stretch for the entire spring. But how much is this little segment getting stretched, the segment of length dx? Well, if dx is 1% of the total length L, then the amount of stretch that this segment gets, dx gets, is only 1% of the total amount of stretch. So this is the total amount of stretch. Right? So how much is the segment dx stretched? You have to multiply that by dx over L. Right? Again, if dx over L is 1%, you're getting 1% of the total stretch. So that is the amount of stretch this little segment gets under the force F. Okay, F is going to be felt everywhere throughout the entire spring. Now, suppose I examine this little segment only, and for this tiny, very short spring, how much is the spring constant? Is that K? No, because K is for the entire spring, which is much longer and therefore much softer. I mean, common sense, right? It's much easier to stretch a very long spring by 1 inch compared with stretching a very short spring by 1 inch, if material is the same, right? How much, so therefore, what is K prime? The amount of stretch, the spring constant for this little segment. I will need that for further studies. Well, by definition, K prime is defined such that when I apply a force F to this little segment, it's going to stretch by a certain amount, which I call dx prime. Okay, dx prime. And as a result, I have F equals to K prime dx prime. K prime is the spring constant for this little segment, and dx prime is the amount of stretch. But this is dx prime right here. This is dx prime right here. This is the amount of stretch. Isn't that what we just got for the the amount of stretch that belongs to this little segment, right? So I can then find K prime. The effective spring constant for this little segment, it is the same F over dx prime. And I know what that is. It is F over F divided by K, and then dx over L, and that equals K times L over dx. Okay, so you see, K prime is much greater than K because it's K multiplied by this factor of L over dx. L over dx. Again, if dx is 1% of L, then L over dx is 100, which means for the same exact spring, if you cut it into 100 pieces and you try to stretch each piece with the same force, you're going to get a lot less amount of stretch. You're going to get 1% of stretch, and therefore the spring constant for that little segment is 100 times as much as the entire spring, all stretched or put together. Makes total sense. Okay, so again, K prime equals K L over dx. This is the first equation I need to know. Okay. So I have found the effective spring constants of this little segment. So now let's use that knowledge and study how this thing moves if I send a wave down. When you send a wave down, every part of the spring will move. And the movement, the displacement associated with that motion is not x. Remember, x is just where the segment originally is without any motion. Right? Every segment will move, and every segment moves by a different amount. Let's say this segment moves by an amount u, and this one by an amount u plus du. Okay, why u plus du? Because they're at different locations. Therefore, they stretch by a different amount at the same moment. Okay, so if the left edge moves by u, the right edge moves by u plus du, then the net movement is du, and therefore that basically says that the entire spring gets longer by an amount du, right? By an amount du. When you stretch a spring by an amount du, how much force do you need to apply? How much force do you need to apply? Well, that is F equals to K prime du. I mean, I'm just applying Hooke's law to this little much shorter spring. The force applied is F, right? I want to know what that F is. Well, you can find that F if you know the spring constant, which is K prime, and you know how much this segment of spring gets longer, which is du. Okay, and so this is just an application of Hooke's law to this little segment, not for the entire spring, but only for this little segment. So that is K L over dx times du, which I can also rewrite as KL partial u over partial x. Okay, why do I do that? Because u, it's a function of both x and t. Okay, the displacement of every part of the spring depends on where that part is and what time it is. But here, when I do this derivative, I am fixing the time t. Okay, both the left and right edge movement u and u plus du are considered at the same moment. And so therefore, the derivative is only with respect to x, not to t. Therefore, it's partial u over partial x. So here is equation number 2. Just basically Hooke's law applied to this segment. Now, how do I continue? Well, remember, the net force acting on this segment is not 0. So that's why the segment can accelerate. Okay, we have a wave motion, it oscillates back and forth, There's certainly an acceleration. What is the net force? Is the net force equal to F? No. F is just how much I stretch on either side, right? You take a spring, you stretch it on either side, the net force is 0, and the spring gets longer as a result, right? But what if the net force is not equal to 0, as should be the case here? Then the net force will cause the entire spring to oscillate, to move, right? I mean, even if the spring doesn't move, because the net force is equal to 0, the spring still gets stretched or compressed, and that's what I saw in equation number 2. But what if the net force is not equal to 0? Then it's going to accelerate. The net force is not F. The net force is F on the right side of x plus dx minus F on the left side, which is x. So that net force is actually dF. Okay, it's df. And that df is what was responsible for the acceleration for this little segment. The little segment is mass dm, and the acceleration is a. So F equals ma, right? Okay, what is dm and what is a? dm is part of the total mass. The total mass is m for the entire spring. And what fraction of m is that? That's dx over L. Again, if dx is 1% of the total L, then this dm is 1% of total mass m. A is the second derivative of the displacement of this little segment. Is the displacement labeled by u or by x? Well, you should know by now that x is not a time-dependent variable. It's just where the segment originally is. U is the displacement. So it should be the second derivative of u with respect to time. Okay, that is the acceleration. So that is equation number 3. Equation number 3 is basically Newton's second law. Now I need to combine equation number 1 and number 2 and number 3. And you notice that the left-hand sides of equation number 2 and 3 are not the same. One is f, the other is df. Okay, the other is df. So what I do is I can plug in f from the second equation, this f from the second equation, into here. Okay, and then I have to differentiate it in order to find df. So let me do that. Okay, so let me combine them. So therefore, instead of df, I can write d of kl partial u partial x, right? That is f, isn't it? From equation number 2. Right? And that equals to m over L times the second derivative u respect to t. And then you have dx. Okay. All right. Now we just have to clean things up a little bit. I have KL, which is a constant. Take that out, and you have d of partial u partial x divided by dx. I'm moving dx from the right hand side downwards, and that equals to m over L partial u partial t squared. But wait a minute, what is this? What is this? Oh, sorry. What is this? This, by definition, from calculus, we know what this is. This is just the second derivative of partial u partial. This is just the first derivative of partial u partial x, which becomes the second derivative. So you have KL squared. Okay, you have KL squared over m. I'm just moving, I'm just moving m and L to decide, and times the second derivative respect to x equals to this. Right? So this is the differential equation that I obtained for the wave motion of a longitudinal wave on a spring. How do I know this is a wave equation? Well, we saw in the video lecture the standard wave equation. The standard wave equation is partial squared y over partial x squared equals 1 over v squared partial squared y partial t squared. That's a standard wave equation, wave on a string, remember? Okay, so you can see we have a very similar structure here. We just replaced y with u, and KL squared over m is v squared, right? If you look at the analogy here, right, you move that v squared to the left-hand side, you will see that. So we know this is a wave. Okay, u is a function of x and t. It's a wave-like function, and the speed of the wave v equals to the square root of KL squared over m. I can write this as L times the square root of k over m. This is the speed of the wave on a spring. Okay, this is not an easy problem, folks, and you probably found that out by now. But through this problem, through this derivation, we have a better understanding, hopefully, what really constitutes a mechanical wave. It's due to different, in this case, due to different interaction of different segments of the spring. They're pushing each other, providing a force. And what I did was I applied Newton's second law. First of all, I isolated this little segment out, this little segment of the spring, isolated, and I found the effective spring constant for this little segment. So I know what happens when it's stretched with a certain force F. And then what if that net force is not equal to 0? It's going to accelerate by virtue of F equals ma. And then I combine these two equations of Hooke's law and Newton's second law. And then I arrive at this wave equation.